So my name is Nina, and in this presentation I describe research done in support of brain mapping. Disorders like TBI or migraines can be better understood if we knew how different regions of the brain intersect and interact. We can segment the brain down to the resolution of a single axon fiber, but training supervised learning models requires annotated data which is hard to manually annotate. So one solution for that is to have an annotation pipeline which can automatically annotate for you by ingesting raw data. NeuroTrail is one such tool, and it can automatically trace long axon fibers by using a model trained in a supervised or self-supervised manner. And the research in this presentation occurs in this red box in the computation layer. The annotation pipeline is agnostic to the type of model it can use and the type of brain data it can annotate. But for this research, we use long fiber projections of axons as seen in this image on the top left. This type of data can be really dense and challenging for neuron reconstruction, but we have been successful in axon tracing of long fibers in dense volumes, as seen from this NeuroTrail axon projection image from one of our previous papers. There are many promising algorithms for axon tracing, but a challenge for a model-agnostic system is to train on new data if needed, and also to improve topological connectivity between long fibers. Topology-preserving loss functions are helpful for ensuring the connectivity of curvilinear segmented objects. I'll describe two such losses here. Seal dice is short for soft centerline dice, and it was developed because of an issue with dice scores during segmentation. Note that the purple segmentation in the top left image does not capture the small vessels as seen in the red segmentation. However, these two different models achieve identical quality in terms of the traditional dice score. From a topological connectivity point of view, the red segmentation is preferred because it captures a greater number of components in the image. Seal dice works well for ensuring topological preservation because it incorporates a notion of topological sensitivity and precision. But the main thing to note is that it uses soft skeletonization for producing morphologically thin structures through an iterative process of min-max pooling, and a major drawback of that is that it requires guesswork and manual tuning of hyperparameters. But applying morphological operations to attain a sense of topological precision and sensitivity is very useful. Warp loss is another topology-preserving loss which works using homotopic warping. The homotopic warping algorithm functions on the principle that given two binary masks with the same topology, one mask can be warped into the other mask by sequential flipping of simple points. That is, points not critical to the topology of the curvilinear structure. In our experiments, we found warp loss to be too computationally expensive for larger inputs of volumetric data. So using morphological operations to compute topological precision and sensitivity is useful for ensuring connectivity. But how to do this for different data sets without manually tuning for each one and ensure that your predicted fibers are the correct length and correctly connected? Our proposed solution is a loss function which applies morphological operations depending on the mean pixel radius of tubular structures in a given sample of data. Our work on this culminates into the two contributions shown here. Next, I'll cover how the proposed methods work. So imagine you have an algorithm for applying a morphological operation. Oftentimes you will need to set a parameter via guesswork to initialize the algorithm, or perhaps you may need to sweep across a range of values. Instead, we developed a method which can intake a volumetric sample from an input data and applies Caney edge detection to find the edges of the curvilinear structures. The algorithm then computes the medial axis transform on the edge detected sample. The medial axis function here computes the medial axis transform of an image as the ridges of its distance transform. Generally, a medial axis transform produces a skeleton where the vertices are found using the distance to the nearest boundary from which they were extracted, and as such they can return that distance during the computation and use it to calculate a mean of such distances. The goal is to minimize the risk of overplaying the operation and losing connectivity between the curvilinear structures. So we use the number of iterations determined by MPR to drive any morphological operation. Here I describe the motivation behind topological smoothing, which we developed to prevent overthinning of axon fibers. As a reminder, here is a small graphic to visually describe the differences between max, min, and average pooling operations. Recall that soft skeletonization applies a series of min and max pooling operations on a given input. we hypothesized that soft scalionization may result in over-thinned outputs, thus reducing topological connectivity. We also suspected that soft scalionization renders output sensitive to affine rotation transformations, thus resulting in lowered evaluation metrics, which motivated us to find an alternative to its min-max pooling ops. So topological smoothing instead applies average pooling operations over an input. We formulated the loss function to still utilize measures of topological precision and topological sensitivity, as we think they are good at capturing the intersection of smooth volumes and inputs used for comparison. And we fixed the alpha to 0.5 for all experiments. I'll just briefly summarize the next two slides. This slide shows the differences in voxel resolution for our datasets using 2D images, and this red region here represents the subregion used for training on DS1. It visualizes also the need for automated tracing, as trying to manually trace even a small volume of brain imagery of this size can take months. The paper describes the training implementation in more detail. Here I'll just mention that the unit architecture we use is from our prior work and consists of convolution layers interspersed with downsampling to form sequentially lower resolution modules in the encoder, followed by upsampling to restore the original resolution for the decoder. There are also lateral skip connections between same resolution encoder and decoder modules. We used 4 resolution blocks to train the unit using different losses, and then performed voxel-wise classification between the output and training images. Here we show 3 iterations of applying a different algorithm for a given input. The main difference between CLDICE and GASC is that GASC is automated via MPR. We see from the histograms that topological smoothing produces an output which is closer to the input. Our trials across different datasets showed that voxel resolution should be considered when choosing to apply a morphological operation, but this effect should be investigated further. We think that lower voxel resolution inputs benefit from topological smoothing. Our ablation study showed that all components of the GATS loss function are required to maximize the CLDICE metric, which, as mentioned earlier, is a useful measure of topological connectivity because of its incorporation of the notions of topological precision and topological sensitivity. Here we visualize the segmentation and centerline detection results of our trained models, and also use the models to automatically annotate volumetric inputs. The GASC result on DS2 shows that MPR is better for ensuring topological connectivity, as it will preclude overthinning due to incorrectly guessed or manually configured hyperparameters. Our results in the Genelia dataset show that maybe there needs to be different strategies for applying morphological ops so as not to degrade the result. Our main observations are shown here again, but mainly we're looking forward to applying MPR and topological smoothing on different data sets and using the GATS loss function to train models built using different architectures. Our goal here is to make an annotation pipeline that is flexible enough to require less additional training when it comes across new data. That concludes this presentation. Thanks for listening.